dear students, class 8 physics. Myself Snell. In the last period, we discussed about all the basic definitions and related phenomena of refraction of light.
In part 2, we are going to learn laws of refraction and effects of refraction. But before
Let
that,
us revise quickly all the points. When light travels from one medium to another medium, its velocity, or we can say its speed, gets changed depending on the optical density of that medium. In the air and vacuum, it travels fastest as compared to all other media. We have learnt when light ray enters from rare medium to the dense medium, it slightly changes its path toward the normal. And when it travels from denser medium to rarer medium, it changes again its path, but this time it bends away from the normal. And in both the cases, light should fall in inclined path. When the light falls exactly normally, that is perpendicular, it remains undeviated. Dear students, we have learnt about incident ray, refracted ray, angle of incidence, angle of refraction and normal. Today, we are going to discuss about laws of refraction. There are two basic laws of refraction. Let us discuss one by one. So, the first law of refraction. When light travels from the two transparent media, the light ray which falls on the surface of both the media is called as incidence ray. The change direction light ray in the another media is called as refracted ray. At the point where it falls, where we will draw a perpendicular, that perpendicular is the normal. And dear students, all these elements, that is incident light ray, refracted light ray and normal, are in the same plane. Just observe this figure. If we will turn this figure, you will notice this very clearly, that these all are in the same plane. Let me turn them. These all are in the same plane. The second law of refraction was discovered by the scientist Snell in the year 1621. In the honor of the scientist, the second law of refraction is given name as Snell's law of refraction. The Snell's law of refraction explains about the relationship between the two angles formed due to the bending of light, that is angle of incidence to the angle of refraction. Let us learn about this relationship of the two angles. For the given pair of media and the given color of light, the ratio of sine of the angle of incidence to the sine of angle of refraction is always constant. We can represent it as sine angle of incidence upon sine angle of refraction. Sine I upon sine R. It is equal to constant, and this constant is known as mu. This constant mu is also referred as refractive index of that media. Let us further discuss the refractive index of the two media in which the light travels. The refractive index of the second media with respect to first media is equal to speed of light in the first media upon speed of light in the second media. Here, if suppose you will consider the first medium is air and the second medium is water, then speed of light in air is 3 into 10 to the power 8 meter per second and speed of light in water is 2.25 into 10 to the power 8 meter per second. So, we will divide this 10 to the power 8, 10 to the power 8 will get cancelled. Here remains 3 upon 2.25. And further, simplifying it, we will get the value of mu as 1.33. So, we can state that refractive index of water with respect to air is 1.33. Similarly, if a light ray travels from air to glass, then value of refractive index is equal to sin I upon sin R. That is speed of light in the first medium, that is air, to the speed of light of second medium, that is glass, equals to 3 into 10 to the power 8 meter per second upon 2 into 10 to the power 8 meter per second. 10 to the power 8, 10 to the power 8 and both the units gets cancelled and we will get the value 3 upon 2. On dividing it, we will get refractive index equal to 1.5. So here we can state that refractive index of glass with respect to air is 1.5. Remember, refractive index of any medium is always equal to or greater than 1. It will never be less than 1. Dear students, now we will discuss certain effects of refraction of light. The first effect, if you will look to the level of water in particular vessel from the top, you will see that the depth of water appears less. And the same if you see little farther, you will see that the depth appears more. Why this happens? Let us observe a practical demonstration. So here, the depth of water in a vessel when seen from air, it appears to be less. Let us take a vessel containing water. Here, its real depth is AO. But when we see vertically above O from air, its depth appears to be AI. It means it is appearing less than that of AO. Reason behind this is a ray of light OA from the point of O at the bottom of vessel is incident normally on the water air surface, that is XY. Since it travels straight path, it remains undeviated. While the second path OB, it is inclined path. OB, when reaches to the surface XY, it bends away from the normal. Remember, here light ray is emerging out from the water to air, means dense medium to the rare medium. And as a result, it gets refracted away from the normal and it goes along the path BC. The two refracted rays AO and BC, when produced back, means if they extended back, they appears to meet at the point I. Appears to meet. Thus I is the image of O, which is virtual image. Thus to observe in air, the depth of vessel appears to be AI instead of AO due to refraction of light from water to air. The apparent depth AI is less than the real depth AO. Dear friends, do you know the real depth by apparent depth is equal to refractive index. Since refractive index of water is 4/3, so its apparent depth is 3/4 of the real depth. Let us see few more activities to understand this effect in the better way.
Activity 1. Take a coin and an empty vessel. Place the coin in the vessel. Put the vessel on a table and step back till the coin is just out of your view. It is hidden from your eye by the edge of the vessel. Now keep your eye in the same position and ask someone to pour water gradually in the vessel. You will find that the coin slowly becomes visible, because then it appears to be slightly raised from the position, that is initial position, to the apparent position. When there is no water in the vessel, the coin is not visible because the ray of light from coin is traveling in the straight line and it does not reach our eye. Let us see simultaneously the same experiment. When water is poured in the vessel, the coin becomes visible because the ray of light from the point A, that is original position, light travels in a straight line and it changes its direction. It bends at the surface of water and reaches our eyes. Thus the light ray bends as it leaves the water and enters our eye. The rays now appears to come from the point B, that is apparent position, and is instead of A position. So in other words, we can say that the coin appears to be raised from the position A to the position B and it appears lifted. This is due to the refraction of light. Let us see activity 2. Take empty beakers or glass, pencils, water. Now keep both the pencils separately in each of the glass obliquely and look at it from the side. In the empty glass, it appears straight. Now, pour water in the second glass up to the brim and notice how the pencil appears. You will notice that a pencil now appears to be bent at the surface of water. This is taking place due to refraction of light. We can explain the reason that the rays of light coming from the tip of pencil, that is C, bends at the surface of water as it enters in the air. It appears to be coming from the point D. In the simple words, we can say that it is due to the refraction of light from water to air, means denser medium to rare medium. When light ray comes out, it moves away from the normal, gives the illusion of bending or breaking of the pencil. Homework. Write answers of questions 13 to 15 from textbook.